Let's solve problem 1.26 from Microelectronic Circuits 8th edition by Sedra and Smith. A particular signal source produces an output of 100 microamps when loaded by a 100 kiloohm resistor and 500 microamps when loaded by a 10 kiloohm resistor. Calculate the Thevenin voltage, Norton current, and source resistance. So let's get started. Let's begin by drawing this signal setup. So we have our source, which includes our source resistance, Rs. Then we've attached some load, RL. And we are reading the output voltage here. And we also have a current, which we'll call IS, our source current. And we can see we're already given some values, right? So we're given different values of RL, their corresponding values of IS. Given these two, we can also calculate the output voltage, right? Because V is equal to IR. So for RL, our first value is 100 kiloohms. Then we have a source current of 100 microamps. And if we multiply these two together, that means we're producing 10 volts. Now we also have 10 kiloohms produces 500 microamps. And this calculates to 5 volts when you multiply R and I. Okay. So you can't really calculate Thevenin and Norton stuff until you know the source resistance. So let's start by trying to solve for that. So how can we solve for our source resistance? Well, let's try to set up equations with values that we already know. That would be RL, IS, and V out. I'm going to use RL and V out. So we know that V out is equal to the source voltage multiplied by RL divided by RS plus RL, because we're only concerned with the voltage across RL. Now what I'm going to do is multiply the right-hand side of the equation by what my calculus teacher calls a fancy one, and it's basically just an expression that has the same value in the numerator and the same value in the denominator, so that it essentially just equals 1, but it will make our algebra easier. Because I'm not really concerned with RL, right? I'm trying to solve for RS. So I'm going to try to simplify this by multiplying the numerator, the denominator, by 1 divided by RL. So again, this expression is just equal to 1. So that's why this is valid. So this simplifies to VS times RL times 1 over RL equals 1. RS times 1 over RL is RS divided by RL. And then RL times 1 over RL is just 1. So hopefully that makes sense of why I did that. So I have two values of RL and I have two values of V out, and that would leave me with two unknown variables. So I'm going to try to make a system of equations. So we'll do this first row of data. So we have VS times 1 divided by RS. In our first row, RL is equal to 100 kiloohms plus 1 equals 10 volts. And in our second row of data, I'm just going to write VS in the numerator now. VS divided by RS divided by 10 kiloohms for our second row plus 1 equals 5 volts. So now I have two equations with two unknown variables, so I should be able to solve for them. So we're going to start by dividing equation, let's divide equation 1 by 2. So on the left side, we will have this fraction divided by this fraction. So we're dividing VS divided by RS over 100 kiloohms plus 1. When we divide two fractions, we can just multiply the reciprocal, right? So that would be multiplied by Rs divided by 10 kilo ohms plus 1 divided by Vs. So these Vs terms get canceled out, and we're just left with Rs divided by 10 kilo ohms plus 1 divided by Rs divided by 100 kilo ohms plus 1. So that's the left side of the equation. And then, the right side is just 10 divided by 5 equals 2. Okay, now I have one equation with one variable. Let me clean some of this up, and then we'll solve for Rs. Okay, let's continue solving this. So I just rewrote the last step over here in red. So I'm going to multiply this denominator to the right side of the equation. So that will become Rs divided by 10 kilo ohms plus 1 is equal to 2 times the denominator now. So Rs divided by 100 kilo ohms plus 1. We can go ahead and distribute that too. So it'll be Rs divided by 10 kilo ohms plus 1 equals 2 Rs divided by 100 kilo ohms plus 2. And I can get rid of these last two fractions by just multiplying everything by a common denominator, which will be 100 kilo ohms. And I'm going to make a note that my final answer will be in kilo ohms because I am going to cancel all these units now. So if we multiply everything by 100 kilo ohms, that'll give us 10 Rs plus 100 on the left side is equal to 2 Rs plus 200 on the right side. Now we can just solve for Rs, so I'll subtract 2 Rs to the left side. 8 Rs, subtract that 100 to the right side is equal to 100. So I get Rs is equal to 100 divided by 8. Plug my calculator. It is 12.5 kilo ohms. Okay, so that is our source resistance. Let me clean this up, and then we'll solve for voltage and current. Okay, let's solve for Thevenin voltage next. What's that going to be? That's just going to be this Vs. So we had our system of equations earlier, but just to recall, right, V out is equal to Vs times RL divided by Rs plus RL. And now I have all the values except for Vs, so I can just solve Vs is equal to V out divided by RL divided by Rs plus RL. And I can choose either two of the cases. I'll just do the first one. So we have Vs is equal to 10 volts divided by RL. In this scenario is 100 kilo ohms divided by Rs, which we calculated to be 12.5 kilo ohms plus another 100 kilo ohms. Get my calculator. Okay, so that is 11.25 volts. So this is our Thevenin voltage. Okay, now what's our Norton current? Well, once you have Thevenin voltage and your Norton current, or sorry, your source resistance, your source resistance is the same as your Thevenin resistance. So you can just do your Norton current. I'll use an N for Norton. Norton current would be just V over R Thevenin, V Thevenin over R Thevenin. So that would be 11.25 volts divided by 12.5 kilo ohms. Could do this math. That is 0.9 milliamps. That's a 0, not a 6. Let me fix that. 0.9 milliamps. So that takes care of the problem.